When you're working on the inequality induction, basically um, questions can be asked in like similar line. When n is higher than when n is higher than or equals to 4, you have to prove this inequality by induction. So let's say the induction inequality is here. It is n factorial is more than 2 raised to n. So we always start with our first step very commonly, like where take n equals to k, and so verify. So when you verify n equals to 4, your basically first number. So you'll get the first number verification as 4 factorial, which is more than 2 raised to 4. So obviously 24 is more than 16. So this verifies our first outcome. Now next is assuming n equals to k is true. So when you assume n equals to k is true, what we get from there is basically 4 factorial, k factorial is higher than 2 raised to k. So you're just going to replace n equals to k in the expression. So n equals to k, if I replace, I get k factorial is greater than 2 to the power k. So k factorial is higher than 2 raised to power k. Now, if I have, this is my assumption, this is assume n equals to k is true. Now, if I take this assumption, then n equals to k plus 1, which means that k plus 1 factorial must be higher than 2 raised to k plus 1. So that's what you is that's what it should be true. So this is k plus 1 factorial is higher than 2 raised to k plus 1. Now, whenever you're doing an equality induction, you always should start with equation first. So let's say I'm going to take the left hand side. So I'm going to take left hand side, so k plus 1 factorial. And I'm going to try to make use of the result which we got, which we assume that it is true. So we assume that k factorial is true. K factorial is higher than 2 raised to k. So this was the assumption statement, and I have to make use of this somehow. So in inequality induction, what we should try is that try to do it with the equation first. Like do something by which you can introduce a similar term like this. So I can rewrite as the left hand side of this n equals to k plus 1 statement. So k plus 1 factorial can be written as k plus 1 times k factorial. It's like 5 factorial is like 5 times 4 factorial, and so on. Now next fragment is how do I introduce the previous part. Now, when you have assume that you have a weighing balance, okay, so let's suppose this is the first band, this is the second band, they are both balancing equally. So when you have um, these two terms here and this term here, they are balancing. What if I replace this k factorial is higher than 2 raised to k. So if I replace this k factorial with a smaller weight, so the smaller weight is 2 raised to k. So if I replace with that, this side will become bigger, because if I'm replacing a higher weight with a smaller weight, this side will tilt. So in this case, what happened is that when I replace um, k factorial with 2 raised to k, my inequality will reverse. My inequality will change to the side because this side has become bigger now. Now, still I haven't got this. Now, still this is not my answer, what I want. Because ideally, what is the left hand side I already got, the right hand side should be 2 raised to k plus 1. So now here's some more reasoning marks required. So what we do is basically we're gonna take as since k plus 1, as since k is greater than 2, k is greater than 4, I can replace k plus 1 with 2, which is a smaller number. So my inequality doesn't get affected still. So as you're going to create the reasoning, since k plus 1 will be higher than higher than or equals to 5. Hence, if I replace this value with a smaller number, let's say 2 or any other smaller number, this inequality is not going to change. So for example, a bigger weight, I replace further with smaller weight, so this inequality holds true. So now since we did that, according to my right hand side, what we get is um, this. So k plus 1, I replace with a smaller number, which is 2, and that results in this final statement. So k plus 1 factorial is higher than 2 to the power k plus 1. So that's how you do inequality induction. Basically, these are the core steps, and obviously you have to write the final step here. So since it is true for n equals to 4, n equals to k, n equals to k plus 1, hence it will be true for n belonging to positive integers, where n is higher than or equals to 4. So that's how you write your final statement. So this is the basic inequality induction. Once again, I'm just going to quickly reiterate the steps. So first you take n equals to k is true. N equals to verification is n equals to for any number, verification is always true. Start it as an equation always, and then introduce the inequality by replacing the n equals to k assumption. And sometimes you have to be extra careful which side the inequality switches. So if this part is not clear, it might create a little bit of trouble. So later on, then you do logical readjustments where you get the reasoning marks. So don't forget to write about this step. So that's how you do the inequality induction. So here is the second question on basically the inequality induction. Now, when you're given a question like this, these questions are at least 8 to 9 marks. So 2n factorial is greater than or equals to 2 raised to n factorial the whole square. So when you do this, you always verify with n equals to 1 or n equals to any given number. So is 2 higher than or equals to 2? That's true. Now our next step is to assume n equals to k is true. So when I assume n equals to k is true, so that's this step. So when you assume n equals to k is true, so you're going to just replace n equals to k here. So according to the assumption, what I get is 2 raised um, to 2n factorial is greater than or equals to, sorry, 2k factorial is greater than or equals to 2 to the power k times k factorial the whole square. Now, if this holds true, so this is your assumption. Uh, Now, if this holds true, what we're gonna do is we have to prove that 2 times k plus 1 factorial is higher than or equals to 2 raised to k plus 1 and k plus 1 factorial, the whole square. So this is what I have to prove eventually. So when we are doing this, I am going to start with my LHS. So LHS is 2k plus 1 factorial. So 2k plus 1 factorial. So basically this is equals to 2k plus 2 factorial overall. And this, as I said, that you always start with the equation induction. Okay, the equation for n equals to k plus 1. So I'm just using my left hand side, and I'm going to just make use of this somehow. So when you do so, you're going to get 2k plus 2 2k plus 1 times 2k factorial. So once we got till here, now again, it's like a weighing balance, which is balancing both the sides. Now what I'm going to simply do is I'm going to replace 2k factorial with a smaller number. Okay, so this side, left hand side, which is 2k plus 2 factorial, now becomes bigger. So this will become bigger since I'm replacing by smaller numbers. So 2k plus 2 as it is, I'm going to keep, times 2k plus 1 n times 2 raised to k k factorial square. So that's where your basic equation has now been introduced to n equals to k plus 1. Next up is that what I want. I want this. I want 2 raised to k plus 1. So if I take 2 common from here, you can clearly see that you basically get 2k plus 2 factorial is greater than, if I take 2 common and multiply with this 2 raised to k, it is going to be 2 raised to k plus 1. So here we are left with k plus 1 times 2k plus 1 times k factorial times k factorial. I'm just writing it twice, this thing, so that I can make use of the inequality identity. So if I write down k plus 1 times k factorial, it is so 2 raised to k plus 1 as it is, times k plus 1 factorial, because if you simply remember, k plus 1 factorial can be written as k plus 1 times k factorial. So you can go reverse way as well. So to get this, so this is something that is the highlight of this question. Now, once you got this step, now if I replace 2k plus 1 is a bigger number, and I replace with a smaller number, k plus 1. So k plus 1, it's not going to, inequality is not going to change. This side still will be bigger. So k times k factorial. So here, that's the reasoning marks. Now see, what I wanted is, I wanted 2 raised to k plus 1. I got it. I wanted one of the k plus 1 factorial. I got it. So my intention was to get other k plus 1 factorial, which is this number. That's why I replaced 2k plus 1 with k plus 1. And you got to say that since 2k plus 1 is bigger than k plus 1, hence I can replace this 2k plus 1 here with k plus 1. So this results in final answer, which is 2 raised to k plus 1 and k factorial, k plus 1 factorial, basically the whole square. So this is how the summary of the entire question goes like. Let's just kind of review once again. So first you verify for n equals to 1. Then you assume n equals to k. Then you have to prove this step. Start as an equation first. So start as equation. So 2k plus 2 factorial is, bring it down so that you can use the n equals to k statement. So after this, you replace with the smaller number. This side becomes bigger than. Now, since now I can take 2 common, so 2 raised to k times 2, and then k plus 1 factorial um, is basically, because k plus 1 times k factorial is k plus 1 factorial, and then 2k plus 1 you replace with a smaller number, a further smaller number, and give the reasoning here, because this carries marks. So k plus 1 times k factorial, that's you're going to be k plus 1 factorial. So this is the summary of this question, and then you have to, don't forget to write down the final statement, since n equals to, it is true for n equals to 1, n equals to k, n equals to k plus 1, hence it will be true for the given statement. So that's how you basically do this question on inequality.